What specific problem does your proposed method aim to solve regarding the understanding of semantic feature evolution in large language models?
Our proposed method addresses the problem of understanding how semantic features evolve across multiple layers in large language models, LLMs. Traditional analyses often focus on single layers or the residual stream, neglecting the multi-layer nature of feature emergence and transformation. By utilizing a data-free approach based on cosine similarity, we align sparse autoencoder, say features across different modules, MLP, attention, and residual, at each layer, allowing us to construct flow graphs that illustrate the birth, propagation, and refinement of features. This method reveals distinct patterns of feature evolution that were previously underexplored, providing insights into how features interact and form computational circuits. Ultimately, our approach enhances the interpretability of LLMs and enables more precise control over their behavior by elucidating the lifespan and transformation of say features across layers.
How does the proposed method work? Illustrate it step by step, explaining how you align the sparse autoencoder features across multiple layers and what the role of cosine similarity plays in this process.
The proposed method aligns sparse autoencoder, say features across multiple layers by utilizing cosine similarity to track the evolution of features throughout the model. First, SAEs are trained at 3 key points in each layer: the output of the attention mechanism, the output of the MLP, and the residual stream. Next, cosine similarity is computed between the decoder weights of SAEs from different layers to identify corresponding features. This involves matching features from one layer to another based on their cosine similarity scores. By constructing flow graphs from these matched features, the method reveals how features originate, propagate, or vanish across layers, effectively illustrating the evolutionary pathways of semantic information. This data-free approach allows for a comprehensive understanding of feature interactions and enhances model steering by enabling targeted manipulation of multiple say features simultaneously.
Can you provide an example of how the flow graph works in practice? Walk through a specific feature's journey through the model layers using your method, highlighting any notable transformations or interactions along the way.
In our study, we illustrate the flow graph's functionality by tracing a specific feature's journey through the model layers, such as a feature originating from the residual stream output, R_L. Initially, we select a feature from the say trained on, R_L, and compute its cosine similarity with the decoder weights of the previous layer's outputs, including the MLP output, M, and attention output, A. For instance, if the feature shows high similarity with an MLP output, we can infer that it has been influenced by the MLP's processing, indicating a transformation where low-level semantics evolve into more complex representations. As we progress through the layers, we construct a flow graph that captures these transformations, revealing how the feature's semantic properties change, such as becoming more abstract or refined. This method allows us to identify potential circuits where MLP and attention modules interact, adding or modifying features, ultimately providing insights into the model's internal computational pathways and enhancing our ability to steer the model effectively.
What are the main theoretical or practical benefits of using your proposed multi-layer steering method with sparse autoencoders over traditional single-layer analyses or steering approaches?
The proposed multi-layer steering method with sparse autoencoders, SAEs, offers several theoretical and practical benefits over traditional single-layer analyses. Firstly, it captures the evolution of features across multiple layers, revealing distinct patterns of feature birth and refinement that single-layer analyses overlook. This allows for a deeper understanding of how features interact and transform within the model, facilitating the identification of computational circuits where MLP and attention modules modify features. Practically, the multi-layer approach enhances model steering by enabling simultaneous targeting of multiple say features, which improves the quality of steering outcomes and reduces hyperparameter sensitivity. Additionally, it allows for smaller cumulative interventions across layers, which can effectively manipulate model behavior without drastically altering the distribution of hidden states, thus preserving core model capabilities. Overall, this method provides a more comprehensive framework for understanding and controlling model behavior in large language models.
How did you validate the effectiveness of your method? What experimental design and metrics were employed to ensure robustness in your findings about feature evolution and model steering?
To validate the effectiveness of our method, we conducted a series of experiments focusing on feature evolution and model steering. We first verified the alignment of cosine similarity relations with actual activation correlations by matching target features in the residual stream with their predecessors across various datasets. We employed a deactivation experiment to measure causal relationships, where we assessed the success rate of deactivating target features by removing their matched predecessors, using metrics like the deactivation success rate and activation change score. For model steering, we compared the effectiveness of multi-layer interventions against single-layer approaches by measuring behavioral scores for topic presence and coherence for language quality, demonstrating that cumulative interventions outperformed single-layer methods. This comprehensive experimental design, including statistical tests like the Mann-Whitney U-test, ensured robustness in our findings regarding the evolution of features and the effectiveness of steering strategies.
What limitations or constraints does your approach have, particularly in its applicability to different model architectures or types of features? How might this impact its broader usage?
Our approach has specific limitations regarding its applicability to different model architectures and types of features. For instance, the method relies on the alignment of hidden state structures across layers, which may not hold true for all models, as seen with the Gemma Scope Attention SAEs trained before a nonlinear transformation at dimension 2048, while MLP and residual SAEs are trained on dimension 2304. Additionally, the effectiveness of our cosine similarity-based feature matching is contingent on the training of SAEs on hidden states that share a compatible structure. Thus, variations in model design could hinder the method's performance. Furthermore, our technique primarily focuses on linear feature circuits and may not adequately capture more complex, nonlinear interactions that could exist in other architectures. These constraints could limit the broader applicability of our method, particularly in models that do not conform to the assumptions of linearity and structural alignment we have established.